Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. This is the last section of the potential control. In this section, we're talking about cycle voltammetry at a fast scanning rate. About the cycle voltammetry, we've been talking in the previous section. And when you got the electric potential scanning back and forth within a certain potential range, the electric potential change and at the electrolyte interface, they might be had the AA charging, discharging current being detected. Definitely it will be, because when you alternate the electric potential, the charge at the electro interface will be changed, and then it still had the current flow through, but that is due to the charge change, the amount of charge changing. You are charging the double layer. The second is they had the electrochemical reaction. The electrochemical reaction will be depends on whether you control at the mass transfer rate or the reaction kinetic controlled. And then the third will be the surface adsorption, desorption. That is independent of mass transfer. And that in this section we are talking about when you electropotential scanning, what the phenomenon observed is the current detected is due to the surface adsorption, desorption. Then let's consider a simple electrochemical reaction, the O to the R. And then when we had the you had the species O dissolved in an ion in an electrolyte. When we surpass the electropotential, then it will be absorbed on the electro surface, and then the reaction taking place, O will be reduced into the R. And then when this one, they had to absorb on the surface before the reaction will be taking place. But when they absorb on the electro surface, then actually create a barrier which other species cannot absorb. Only this area is open, available for other species to absorb on the surface. The brown line means the electron covered by adsorbed species here. So when you electropotential keep going scanning to other potential, the surface was covered by the absorbed oxide. Eventually, the entire surface will be covered by the adsorbed species. At the beginning, the adsorbed species is not covered the electro surface. That we said that the coverage, the surface coverage, the gamma O equal to 0. When the electro surface was completely covered by the adsorbed species, and then the gamma O is equal to 1. The gamma actually is surface coverage of the O species. So then we can make a material balance at the electro surface. So the gamma O as a function of time, when it keep changing, when we electropotential scanning from one location to the other location, and then when you scan, they keep absorbed. So the current detected is the adsorption of the O species and reduced into R. And then R species absorbed on the surface, it might be released, dissolved from the surface. So this one we can, from the unit balance, you can see the adsorption of the O species is more of O per centimeter square, how the surface coverage, and per unit time, how much the O on the surface was absorbed or dissolved. And equal to the current is the coulomb per second, the amperage, and the N is how much the balance per mole of O reactor, how much more of electron need. So this N over here, and then Faraday constant per mole of electron, how many coulomb here, and then constant the electron area. So from here you can see more electron will cancel out, and then the more the centimeter put over here, and the coolant was cancelled out. So you end up with more of O per centimeter square per second here. So by analytical solution, you will end up with the current density against a function of time. When the electric potential scan from this direction, the current will go through a peak current and drop out. Because when you got the electric potential scanning more positive, for instance, in this case, the current keep going because the reaction keep getting faster. But when at a certain location, the entire surface, majority of surface are covered by adsorption species. The further there's no more adsorption species available to absorb, like a parking space, and the most parking area was occupied by the vehicle. Then there's no more vacancy for new coming vehicle. So the current will keep dropping until the entire surface was covered by the adsorption species. The reaction actually ceased. And it depends on the scan rate, the current you observe might be different. One thing you had to be noticed, the adsorption of the adsorption of this kind of behavior, actual current is quite small. It's a microamp, because as long as the entire surface was covered by the adsorbing species, the reaction ceased. So there's no mass transfer reaction continue supplied. So it's only the surface phenomenon. So the current actually observed is very low. Over here we can see the surface adsorption phenomenon by the material balance, and the Faraday is low here. And then the entire surface actually is equal to 1, either covered by the oxide species or reductant species. The overall they always remain constant here. And the surface covered by the ratio of O species to the R, the surface coverage is equal to the O oxide species in the concentration on the electron surface, and the ratio O to R. And that's the equilibrium, the equilibrium constant over here. This means that the O species in a solution will be continuously keep equilibrium to the surface O species on the surface. On the surface will keep some kind of equilibrium relationship here. And this one will be talked about in the next slide. So there would remain an equilibrium stage between the concentration on the electron surface and then adsorption on the surface. So, and then the solution concentration on the surface and obey the Nernst equation. So the potential change will be alternate the concentration at the electron surface, and at the electron surface will be change the ratio of the adsorption species on the electron. So by substitute those kind of balance electron and then to the current, then we end up with this kind of equation, something like that. And then the plot of this one, you can see the current as a function of electron potential, the current as a function of electron potential. They always go through the peak potential, peak current here, and over here there's the potential, the peak potential maybe somewhere around here, and depends on the scanning rate. Higher scanning rate, you got a higher peak current here. We talk about equilibrium. That means in a solution, the oxide species or reductant species in a solution right at the electron surface they remain the equilibrium with those species adsorb on the electron surface. The equilibrium constant, something like BO and then BR. We can see at the electrode surface, the all oxide that will be gradually adsorbed on the surface from a bonding, certain kind of bonding, and then the activity of the oxide in the bulk, we say the AI bulk, and then the AI adsorbed species. In this case, we saw the gamma O, and then they should be maintain certain kind of equilibrium over here, because the adsorption is so quickly. They always maintain certain kind of equilibrium. How much at the electrode surface in the bulk solution, they'll be equivalent with the adsorb on the surface. This can be derived by the electrochemical potential. We call the mu I. We call it the electrochemical potential here. The electrochemical potential at the equilibrium, that means in the bulk, always maintain equilibrium with the species adsorbed on the surface over here. So the A means the adsorption species, and the bulk is at the electrode surface still remain in the solution. So, and so this one can be written in this direction, this equation. This means at the unit activity or in other activities. This is similar like a Nernst equation. In the adsorption species and in the bulk, there shall be like a Nernst equation. This is at a standard condition where the activity equal to 1. The same thing over here. So, and then at a standard condition, this is at a standard unit activity condition, we can say it's a standard free energy here, the difference. So we can write in this direction, this way. So substitute this delta G into here, this equation, we end with like this. And then, so we can further reduce this equation, write rearrange the equation. We can say something like that. And so it ends with adsorption of I species or O species is equilibrium with the adsorption species in the bulk. And there's a constant here. The constant is this one here. So so this one, when the electron potential scan from one direction at a different scan rate, we get this the current behavior. When we got it, and then this so the peak current, it corresponds to how much the maximum the oxide can be absorbed on the surface here, and then the scanning rate here. So the peak current is a proportion to the scanning rate, you can see here. And then the peak potential here will be depends on their equilibrium over here, the adsorption O on the R species. So that's and when we electron potential are scanning backwards, then the reverse for scanning rate, we got corresponding the peak potential. If this is the reversible reaction, the adsorption speed reaction is very fast. In that case, the peak potential for the forward scan and backward scan, they almost should be the same at the peak potential here. But if the adsorption reaction is kind of sluggish, slow, then the peak potential may be, the forward reaction may be shifted in this direction, and the reverse reaction, the peak potential will be shifted in this direction. And if you get a faster scanning rate, that shift, the potential difference will be greater. So for hydrogen adsorption on the platinum surface, keep this in mind. Then actually we should get the total peak, because on the hydrogen adsorption on the platinum, it might be depends on crystal structure. So usually they have 3 peak at say the crystal 100 and 110 and 111. The different crystal structure, they had a combination of these 3 peak, and it's come up with something overall the peak behavior, something like that. This is real the platinum soaked in a sulfuric acid, and then we scan the potential from here to this direction and come back. So when the potential at a very negative location, on the platinum surface is negative charged. So the water adsorption on the surface, they will be oriented at hydrogen, the positive end will be adsorbed on the surface. So you got the hydrogen adsorption, you got the 3 peak this direction. When the potential gradually shift to the more positive direction, then the charge, the negative charge gradually reduced, and then the water will be shifted oriented corresponding to the charge balance. In this region is a double layer charging. That means there's no electrochemical adsorption or any electrochemical reaction, only the charge balance like a double layer charging. So there's a double layer charging current here. And then when in an electro potential at a very positive location, the surface was loaded with positive charge, then the water molecule will be oriented with negative oxide adsorbed on the surface. So this is a bunch of oxide surface peak adsorbed on the surface. When the potential is scanning back, then the entire all the oxide adsorbed on the surface will be reduced right here. And then over here, the electron potential, this is also considered double layer charging also. Then from the positive to negative, then the water will be oriented to the hydrogen side adsorbed on the surface, and the hydrogen adsorption initiated in this position. Over here, actually, this is distinguished peak over here, because only the platinum will be adsorbed. The hydrogen will be adsorbed on the platinum because it's a very active platinum catalyst. For the carbon, actually, they don't have this kind of adsorption behavior. On the carbon only had a double layer charging. On the platinum, they had the hydrogen adsorption and oxide formation over here. Usually, people can use this area can be estimated how much the catalyst was adsorbed on catalyst area, because this corresponding how much the hydrogen was adsorbed on the surface. If they all cover up entire the catalyst surface, then each one how much area will be theoretical can be calculated. Then this one actually tell you how much platinum active surface was on the surface. People use this one area to estimate how much catalyst area. Over here, actually, is this axis is a potential, but don't forget, it's also is indication of a time scale, because when we migrate the electron potential shift from here to scanning from here to this direction, actually time also change from here to here. So this one you can see is a time axis, the time spent on travel from this potential to this potential, the time spent, and then the time times the current here, it give you a total charge, how much the hydrogen was adsorbed on the surface. So for the gold, on the gold actually there's no hydrogen adsorption or desorption, but they do have the oxide formation and over reduction. So you can see actually if you scan at a different ending potential scanning back, you had more oxide formed on the surface, then they will totally reduce here. The area here and to the area here almost 1-to-1. So if you scan them, the potential at this region, then you got a more higher reduction current over here. When the cycle voltammetry can be applicable for the fuel cell, usually people use to estimate the actually platinum area, available platinum area in the catalyst layer. because right now the fuel cell is special like a pen fuel cell. The electro catalyst was use the platinum like the brighter dark, a brighter spot. The dot line is a platinum, and then this is the carbon. They deposit on the carbon. If you use a conventional surface area detect technique like a nitrogen adsorption, they call the BET method. Actually, you are detecting the entire surface because the nitrogen adsorption they cannot distinguish the catalyst or the carbon surface. They give you the entire surface area. But for the fuel cell, only the platinum is really active surface area. So if you use a cyclic voltammetry, you measure the actually is the active area of the platinum rather than the carbon area, because hydrogen adsorption only taking place at the platinum area. In the carbon area, actually nothing going to happen. Only the double layer charging current may be happen. In this way, you can distinguish what the real available platinum area in the catalyst region. This photo was taken from this paper. So if I'm interested, you can see this paper. So over here, you can see for the typical platinum, if they treat the catalyst, they prepare at a different preparation for the electro recipe, even the pretreatment at a different anion temperature, all those kind of things. You will see the area will be different cyclic voltammetry. So you can see this area with the same amount of catalyst, but which if you treat at different temperature or different recipe, the electroactive area will be different. So from here you can see can pick out the best electro recipe on the treatment for the making the catalyst layer. And also over here you can see this is a pure platinum without carbon, so the double layer charging area very small. But with the catalyst with the carbon, you can see this is a platinum over here, and this other area is a carbon. So the cyclic voltammetry with the platinum load on the carbon, it might become like this. The double layer charging current in this region become very wide because most area is a carbon area. The platinum only come over here. So over here you can see from here you can estimate how much available platinum catalyst layer in the catalyst layer here.